Okay, young students of chemistry. So today is the day where we put our stoichiometric calculations from last unit into our gas calculations from this unit. I have two problems, or three example problems I'm going to do here with you. And then you have a series of five problems that are on a half sheet of paper where you can practice this. So we had talked about this a little bit earlier, maybe even last unit, that under certain conditions, when you have unchanging temperature and pressure, we can treat those mole ratios as volume ratios. This is an extremely rare circumstance. It is not often that the temperature and the pressure are not changing. But when that does happen, it makes for a nice, easy problem for you, because all you have to do is apply a mole ratio. So we can see here, if we have 5 liters of hydrogen reacting with 4 liters of oxygen, we can determine very quickly that the limiting reagent is the hydrogen. Remember, we'll divide that 5 by the 2. That gives us 2.5, which is smaller than 4 divided by 1. Which means that this goes down by 5. And the water is going to go up by 5 times 2 over 2. Which is what? So we will be getting 5 liters of water from this reaction. That's as simple as it gets, and as I said, those are extremely rare circumstances. More commonly is we'll start a stoichiometric calculation with some non-gaseous substance, and then we'll be solving for the volume of the gas. So to do that, of course, we'll use we'll get moles. If it's solid, we use the molar mass to get moles. And then, of course, we'll go from moles of our non-gaseous substance to moles of our gas using our pH chart. And then after we have moles of gas, we'll use PV equals nRT, the ideal gas law, to figure out the volume of that gas. So nothing different. Get moles of your gas, and then use the ideal gas law is the only thing we're tagging onto that. If we're starting with a gas and we're solving for a non-gaseous substance, of course we know we have to get moles. If it's at standard temperature and pressure, we've been doing this for this is the third unit now. Excuse me. 1 mole of gas is 22.4 liters. If it is at non-standard temperature and pressure, this is where we'll get moles using our ideal gas law. We'll solve for moles of the gas using the ideal gas law, and then we'll use BDA to get from moles of the gas to moles of the non-gas, and then, of course, to solve for whatever unit that they ask you to solve for. Generally it's grams, because that's a very measurable unit. Okay, I'm going to do 2 problems with you. So the first example, potassium chlorate is decomposing. So the first thing we should do is write the equation for the decomposition of potassium chlorate. We know that metal chlorates will decompose into metal chlorides, and oxygen, what? Gas. Let's see, this balances with a 3 here, 2, and 2. Okay, it says when potassium chlorate decomposes, 755 milliliters of mercury is the pressure, and 23 degrees Celsius, 42.6 milliliters of gas is collected. How much potassium chlorate must have decomposed if none of the gas was lost? So we're solving for the amount of potassium chlorate that decomposed, and they're assuming that none of that gas was lost, which you guys know is not always the case when you perform an experiment. So we're starting with a gas, and we're going to a non-gaseous substance. So we're going to get moles, and this time we're going to get moles by using our ideal gas law. So moles of oxygen, remember it's the ideal gas law, we have to use that for gases. Let's see, PV equals nRT, so N is equal to PV over RT. exact value for R. R is on the bottom, so I'll put 0.0821 atmospheres times liters over moles kelvins. And now we have to make sure all of our units are in the proper form. So our pressure has to be in atmospheres. It is not, so we're going to want to convert that. 755 milliliters of mercury. We know that 1 atmosphere is 760 millimeters of mercury. So we've got a little bit less than an atmosphere of pressure here. Sorry, put your questions down in your calculator. I'm showing a pressure of 0.993 atmospheres. According to the universal gas constant, the volume of our gas needs to be in liters. So we'll move our decimal place over 3 places to get liters. And now I think we have all the information. Oh, no. Celsius, of course, has to be in Kelvin. So 23 plus 273. Please forgive me. And it's 296 Kelvin. Better put that 0.0 on there. Okay, now we can plug our values into our equation. The pressure was 0.993 atmospheres. The volume was 0.0426 liters. And then R is on the bottom. The temperature was 296 Kelvin. Chuck that on the calculator. I'm getting moles of oxygen is 0.00174 to 3 significant digits. And that's what goes down here. Which means that this must have gone up. Which means this must have gone up. Yep, oops. Yeah, sorry. Times that mole fraction, 2/3. So it looks like originally we started with 0.00116 moles of potassium chlorate. And we've answered the question. How much? Of course, probably best to put that into grams. I'm not going to do that right now. If you'd like to do that, check with each other to make sure you have the right amount. Okay, second one I'm going to do with you here. And then you're on your own to complete this 5. And we'll do a lab on this. We're going to decompose some copper 2 carbonate basic. Okay, it says magnesium replaces hydrogen when it reacts with hydrochloric acid. So this is a single replacement reaction. Magnesium plus hydrochloric acid equals, and we know that that's going to be magnesium chloride and hydrogen gas. 4.02 grams of magnesium reacts. What volume of hydrogen will be formed at those particular conditions? Notice that these are not standard temperature and pressure, so we're going to have to use our ideal gas law. Okay, but first we have to get moles. Always get moles. 4.02 grams of magnesium. Molar mass of magnesium is 24.31. That gives us 0.165 moles of magnesium. And we are solving for what volume down here, and then plug that into our ideal gas law. We know that these start at 0, this always goes down, these always go up, and then this is going to go down by 0.165 moles to get us 0, which means this is going to go up by 0.165 moles. Oh, never balanced the equation. That's kind of important. Let's go back and do that. Let's see, we need a 2. But that's it. So our mole ratio then is 1 to 1. And that's our moles of hydrogen. Now we can use the ideal gas law to solve for the volume. Our volume is equal to nRT divided by P. Algebra first, people. I want to see you cancel the units. This is the volume of hydrogen gas. I like to put that there as a reminder and make sure that you're solving for an actual gas. You're using the ideal gas law to solve for the volume of a gas, because sometimes students will put all sorts of non-gaseous substance into that law. So just be careful with that. That's why I like to put that little A, what am I solving for? The moles of our hydrogen are 0.165 moles. Of course, the value for R, the universal gas constant, 0.0821 atmospheres times liters over moles kelvins. The temperature, 25 degrees Celsius, in kelvins is 298. And then the pressure is in kilopascals. We're going to have to convert that to atmospheres. So 115.0 kilopascals. And 1 atmosphere is 101.325 kilopascals. Oops. So 115. And 1 point, what do we have here? 4 single digits. I'm getting 1.135 atmospheres. You guys should always verify my calculations. There we go. And now our moles cancel. Kelvins cancel. Atmospheres cancel. And we have liters of hydrogen gas. Doing 3 single digits, I'm going to need 3.56 liters of hydrogen. And that would make quite a hydrogen balloon. That would be loads of fun. Just a reminder if I assign points to these problems, so you know. Remember, it's always 1 point for reactants, 2 points for products. It's going to be 1 point for getting your moles, 1 point for your mole ratios, and then 1 point for your hydrogen. I'll probably also give points for conversions here to atmospheres. And then 1 point for the algebra. Excuse me. 1 point for the substitution with the units. No units, no point. 1 point for the answer. So this problem we're looking at 1, 2, 3, 4, 5, 6, 7, 8, 9 points. Okay, you have a problem set. I think many of those problems, I'm not looking at it right now, but I think many of those problems are percent yield problem, so you're solving for the theoretical yield and you're given the actual yield. Don't let that confuse you. Separate those out. You'll solve in this manner for the actual yield and then do actual divided by theoretical times 100. Okay, so tomorrow we will switch the calendar around a little bit. So what was on the calendar for today, which was Graham's law of effusion or diffusion, we'll do that lab tomorrow. I'll give you some time to ask me some questions on these gas stoichiometry problems, and then we'll do your lab on gas stoichiometry and finish up the unit with solids and liquids, condensed states of matter. All right, I hope you have a great day.